Okay, on Thursday. Thanks for reminding me. Hopefully my calendar was going to give me an update or whatever. Yes, okay. So if it says that on the syllabus, we're going to do it. We haven't had a lot of class yet, but it just means you have less material to worry about for the first quiz. And yeah, so as a reminder, the quizzes are not problem solving. They're just like short answer questions about stuff I said in the notes. So like we've talked about mostly just vectors so far, you know. Does, you know, which one does order matter for, cross product or dot product? And you do your answer, that kind of stuff. That's right. Yep. Yes.
So we shouldn't expect any homework from.
Right. The quizzes will never have any kind of calculations. And then that's all that'll be on the exams is problem solving. Okay. Any other questions? All right. Well, we're done with the vector review. And so now we're going on to particle statics. And so a particle is not a actual thing. No thing is inherently a particle. A particle means a mathematical model of something. It's the way we're treating something. And it's when we treat an object as having no length dimensions. And therefore, its orientation doesn't matter. I mean, if I'm going to say therefore, it's like its orientation can't be calculated. And so you treat things like particles where you don't care about the orientation. So we only use the particle assumption when orientation doesn't matter. This is kind of an interesting thing to notice. If you're using Newtonian methods, which is what we're doing in this class almost the whole time, if you're using Newton's laws to calculate things and you're dealing with forces and accelerations and stuff, you can treat anything as a particle and it doesn't mess up your calculations. It just doesn't let you calculate orientations. That's not true if you're using energy approaches. With energy approaches, since rotational kinetic energy and translational kinetic energy are both kind of representations of the same total energy, you can't just skip one and do the other one, you know? So I don't know. In Newtonian mechanics, you can treat anything as a particle. as a particle. You just don't get orientation information, which is a big, that's a big thing to give up in a lot of cases. Um, but if you're doing an energy approach, if the thing has significant um, rotational energy, which usually just comes along with having a significant mass moment of inertia, then you have to take that into account. So, for example, if you if you're trying to calculate the if you're trying to calculate how fast a wheel is going to roll down a ramp, okay, uh, you might think like, oh well, I don't. All I care about is the translation of the center of the wheel, so I'm just going to use an energy approach, calculate, do it like a skier skiing down a hill or whatever. Well, if you did that, you'd get too high of a velocity for the wheel at the bottom of the hill, and that's because some of the energy that comes from the potential energy gets transferred into rotational kinetic energy. It doesn't all get transferred into kinetic energy. Okay. I can't make myself stop talking about this. It's not really that important. It's just sort of an interesting thing. Like you get in this thing. It's not just me, I don't think. It's like you say something and you're like, I didn't say that very clearly, and then so you say it again, and then you're like, I got to make this clear, and then it just like ruins the whole class. Yeah. Okay, I'm gonna get it back together right now. Um, in particle in particle statics, since we don't care about orientation, uh, the governing equation is Newton's second law, which I always abbreviate N2L. And we will, so if it's static and there's no acceleration, that says that the sum of all the forces acting on a body is equal to the zero vector. How many equations does this give us? In a 2D problem, this gives us 2 equations. And in a 3D problem, we get 3 equations. Okay, that's pretty, seems pretty obvious when we're dealing with Newton's second law. When we start including the moment equation too, we're going to see the surprising fact that we have 3 total equations in 2D and 6 total equations in 3D. We'll get to that. And anytime we use this, so anytime we use Newton's second law, and that's all we're using for particle statics, but this is also true of the moment equation. I require you to draw a free body diagram, and I'll take off points if you don't, and if you lose points for not doing it, you're going to be really annoyed at me, but it's going to, if you do this, you're going to be happy that you've built this habit. So you must draw a free body diagram. And the thing is that, since in your earlier mechanics classes, you do simple, relatively simple problems, you can do all the bookkeeping in your head, and the benefit of free body diagrams isn't always like super obvious at first. But when we get to complicated problems, you'll be glad if you built these habits. So a free body diagram. Here's how to do it. Um, so first, draw closed outline of the body you've chosen to isolate. Um, and we want to, so the free in free body means that we're replacing any surrounding things, anything that is not part of what we're isolating. We're only including those as forces. Okay, so we're not going to include any external objects in this outline, and no internal details. Okay, so for example, let's say that we're going to isolate this car. And the car is sitting on the ground. And I was going to draw a cat, but better drawing pigs. Okay, so there's a pig on the roof. Actually, that looks like a cat. And there's like a rope connected to the back that's being pulled by this helicopter. Okay, we're going to isolate the car. Okay. So all we're doing is drawing a closed outline of the car. Okay, that's what we draw. Not, so this, not this, because that has internal details. And all we're trying to do is be very clear to ourselves and whoever is looking at this, that this is the boundary that defines the stuff on the inside of the boundary as our chosen system, and the stuff outside the boundary as the outside world. Okay? The whole point of the free body diagram is just to be clear of what's in the in crowd and what's out. Okay? So don't draw the wheels, don't draw the ground. Okay, the ground is an external detail. And it has to be a closed outline because this boundary is the key idea to this. So that does not, that's not a closed outline. And so in a complicated problem, what are we including here? Just the underside of the car, or is this supposed to be the whole front and back part of the body? So we just want to be very clear in our picture what's inside the chosen object and what's outside. Why do we want to do that? Why is it so important? Because everything applies forces to everything else, you know? And so if we're not including the metal here and here, okay, then that metal is applying forces to the bottom of the car. And so being clear about what's inside and what's outside is necessary to figure out where there are forces from the outside going in and when those forces are internal and we don't have to deal with them. Okay. Step 2. Draw all the loads that are applied to the chosen object by the outside world. And we'll break these up into forces with unknown directions, and forces with known directions. So if you have forces with unknown directions, I'll make this 2A. And when I say forces, I guess what I really mean is so loads broken up into about this. So I want to be more general than forces. Loads are made up of forces and couples. So let's that is loads. For now, we're only dealing with forces because we're only dealing with particle statics. Loads with known directions. And then this is loads. Okay, so if you have an unknown force direction, draw 2 small arrows in the direction of the coordinate axes. So it would be like this, or a lot of times you see people do it like this. Either one of those is fine. And label with a force with a vector variable. Okay, so this we would label with like an R or an F or something like that. Okay, what that's saying is that this force R is made up of a X component, R, and a Y component. So like Rx and Ry. Loads with known directions. just draw an arrow in the known direction. And label it with a scalar variable. Okay, so if you know that the force is acting in that direction, all that needs is, it depends what kind of variable it is, what you're probably going to call it. But so why is it? So what this is saying is if we have a force with an unknown direction, it's represented by two variables in 2D or three variables in 3D. And if we have a known direction, it's represented by a single variable. Why is it that if we know the direction, we can represent it with a single variable like that? Mathematically. The unit vector, that's right. Because if we know the direction, we're going to have this thing, this variable, multiplied by a unit vector that defines that direction. And so then this is all we have to solve for. If we don't know anything about it, we have to solve for two variables, or three in 3D. Any other questions about that? Because I'm stupid. To be, and then what else is wrong? I said something about, well, right here, I'm sort of thinking of all this in terms of 2D problems. That's what we'll do most of. But in 3D problems, you'll draw three axis directions. Okay. So let's just do a particle statics problem. So let's say that there is a mass of 10 kilograms. And it's connected to two walls by cables. And let's say that the center of mass of this mass is at the origin. And let's say that this cable connection is at the point -2, 1. All this is in meters. And let's say this one is in the spot +2, 1. What are the cable tensions? Okay, so the thing we want to isolate is the mass. Whenever you're doing problems that are like from a textbook or problems that I give you or whatever, if only one of the objects is given a mass, that's probably the thing you want to isolate because you're almost always going to include weight in your calculations. So that doesn't work in like real problems where you're defining it from the world or whatever, but in any kind of cooked up problem, that's probably a hint that that's what you want to isolate. Okay, and what forces are acting on this thing? One way to think about this, I mean, in a problem, this is a pretty simple problem, but as problems get more complicated, sometimes it can be hard to figure out like when you're done, when you've dealt with all the forces. And I think it really helps to think about it this way. The only types of forces that you ever have to deal with are field forces, which is usually gravity, but it could also be like a magnetic field or electric field. In this case, it's only the weight. So deal with the weight force, and then just go around the boundary. This is why this outline thing is so important. Just go around the whole boundary and just look for the places where the outside world contacts the boundary. In 3D, you have to imagine the whole thing. You know, it's easier in 2D because you're just going around that path. But the only other place that forces can act are where the outside world touches it. Okay, so there's one here, and then we know we're done. Okay. By the way, I think this is interesting. Why is it that we only care about, like, when you define Newton's second law, it says that add up all the forces on the body, and then that's equal to the mass times the acceleration. Why is it that now in practice we only care about the forces that are applied to the body by the outside world? You know, there's whatever millions of molecules in there bouncing off each other, they're applying forces. What is it about those outside forces? Well, it's not that. They don't have to be more relevant. The thing is, Newton's third law says each force that object A applies to object B, right? Object B applies an equal and opposite force to A. And so if those 2 points, A and B, are both inside our object, every pair of internal forces cancels out. Okay? So this molecule here applies a force this way to that one, and that means that this one applies a force that way to this. The only place where that doesn't happen is on the boundary, because like over here, the cable applies a force this way to that molecule. This molecule applies a force this way to that cable, but we're not including forces applied to the cable, only forces applied to the body. So all of the stuff happening internally is all cancels out and it doesn't come into the calculations because of Newton's third law. And all we're left with is the outside world applying forces to the boundary. Okay, so the weight is 10 kilograms times 9.81, so 98.1 newtons. And then we have a cable force going this way. I'll call that T1. And we have a cable force this way. I'll call that T2. Since those are acting in known directions, those are just scalar variables. So now let's think about how to represent these as force vectors, because we're going to need to represent them as vector components to put them into the equation. So how are we going to get a unit vector for this one? Yep. Yeah, right. So we need to come up with this, and there's 2 ways we can do it in 2D. We can use an angle, or we can subtract the coordinates if we have them. In this case, we're given the coordinates, so we might as well just subtract them. So I'll write it as the vector u in that, a vector that's in that direction, but it's not a unit vector yet, is equal to 2, 1 minus 0, 0. And so that's 2, 1. The magnitude of u is 2 squared plus 1 squared square root, so that's root 5. And so the unit vector is 2 over square root of 5, 1 over square root of 5. And so the force vector, when we write it, is just going to be that's just going to be, I'll write it as 2t over root 5 T1, and then 1 times T1 over root 5. And this one's similar. But the same way, you get that this force vector is going to be negative 2 T2 over root 5 and positive T2 over root 5. So now we can go to Newton's second law. We're going to add up these two forces with the weight force. So we have 0, negative 98.1, plus 2T1 over root 5, T1 over root 5, plus negative 2T2 over root 5, T2 over root 5. And this isn't accelerating, it's just hanging there, so that's equal to zeros. So from the x equation, we get that 2T1 over root 5 is equal to 2T2 over root 5. Oh, so 0 plus 2T1 over root 5 minus 2T2 over root 5 is equal to 0. That's the x equation. And that just tells us that T1 is equal to T2. And then we'll use that in the second equation that says negative 98.1 plus T1 over root 5 plus, I'll substitute T1 in again for T2. T1 over root 5 is equal to 0. And then we can calculate T1 is equal to, you get about 109.73 newtons. And then that's also equal to T2 because we found out those have to be the same. What? Yeah, because I substituted. So from the x equation, we got the T1 and T2 are the same. And so then I substituted T1 in for T2 in the second equation. Any other questions? Notice cables can only pull on things. And so you should know at the start of a problem with cables what direction that cable force is. And so if you ever get a negative value for a cable tension, something went wrong. And it's a hint that you need to look back and find where the mistake is. And when something goes wrong like that, it's sort of a common natural thing to just say like, well, I know this should be positive, so just cut off the negative. And don't do that though. when something like that goes wrong, that's one of the rare places where you have information that lets you check whether your steps went right or wrong. Most of the time, you can't really do that. All you can do is like recalculate the problem or whatever. But this is a case where something is giving you a hint that one of your steps went wrong. Okay. And so take that opportunity. They don't come up very often to go back through your steps and find where the thing went wrong. Sometimes it is true that like you just have a negative wrong and it comes out positive. But a lot of times it helps you find something bigger than that. Okay. Um, so let's do a pulley advantage problem. So let's say that there's a ceiling and we have two pulleys attached to the ceiling like that. And then two pulleys that are hanging from the cable. And those are supporting a mass. Let's say that mass is 100 kilograms. And we have a cable that's attached to the ceiling over here, and then strings through this system of 4 pulleys. And we want to calculate how hard you have to pull on that cable. What does that cable tension have to be so that that 100 kilogram mass doesn't accelerate? Okay, so this idea is called Pulley Advantage. And in certain configurations of multiple pulleys, you can get this effect where you can support a large mass by applying a small force to the cable. It's kind of amazing how it works. The more pulleys you have, if they're frictionless and massless, which is not, that can't really happen. So at some point you get diminishing returns. But the more pulleys you have, if you rig them up in the right orientation, in the right, do it in the right way, you can get smaller and smaller values required for this tension key. It's not the pulleys themselves that do it, it's coming up with the right configuration. So pulley advantage isn't an inherent thing in a pulley. It's something you can do if you use the pulleys in a certain way. Just a single pulley itself doesn't reduce the required force. All it does is change the direction of the force, Okay, let's calculate this. Okay, so the first question is, what do we want to isolate? And it turns out to be easiest if you isolate everything that's hanging from the cable. So the hanging stuff. So what does that look like? So it's those two pulleys and then the 100 kilogram mass. And the forces acting on this chosen system, we're assuming all these pulleys are massless, so the only mass is the 100 kilograms. So there's a downward force of 100 times 9.81. So that's 981 newtons. And now go around the boundary of this system looking for where the outside world makes contact. Where does that happen? Where does the outside world make contact with this boundary? At the two pulleys, and on each of those pulleys, it happens at two spots. Okay, so the cable is pulling away there. It's pulling away there, and there, and there. And this is all the same cable. All it's doing is stringing through these pulleys. And that means that the cable tension has to be the same all the way along its length. So all of these have a value T. Any questions so far? And then Newton's second law says, so we have a weight force of 0, negative 981. And then we're adding to that 4 cable forces in the positive y direction. So 0t plus 0t plus 0t plus 0t. And we're trying to calculate what that tension is when this isn't accelerating at all. So set this equal to 0. The x equation doesn't give us anything. It just tells us 0 equals 0. We already knew that. And then the y equation says negative 981 plus 4t is equal to 0. And so solve this second equation, and you get that t is equal to 245.25, I think, newtons. So if you set up this configuration with a mass that's being supported by hanging pulleys, and it's being lifted relative to two other pulleys that are connected to the ceiling, and well, it doesn't have to be two. You just have to have the same number of hanging pulleys that you have pulleys attached to the ceiling. What we're doing is holding up a 981 Newton weight by applying a force, holding onto the cable with a force of 245 newtons. That, obviously that's a really useful thing in a lot of applications, and so that's used in a lot of places where big loads have to be lifted into trains or ships or whatever. And I think there's at least one problem on the homework coming up where you have to do something like that. There is a trade-off. There's always conservation of energy says there always has to be some kind of trade-off. And the trade-off is, excuse me, well, if you're just holding it up, then that's fine, because how much work are you doing when you're just holding something in place? None. But if you want to use this setup to lift this thing up, the trade-off is, think about this, to pull your little part of the rope down 1 inch, you have to, that inch is coming from all 4 of these things. And so you can think of that as like pulling this down 1 inch means shortening each one of these 4 things 1/4 inch. Okay. And so to get this to go up a distance, you have to pull this 4 times as far. That's conservation of energy, so you can't get energy for free. And so instead of getting that same amount of energy with the big force, you're getting that big amount of energy with a bigger displacement. But a lot of times that's still a trade-off you're happy to make, And also, you could use this as a way to catch really big fish on weak test line or whatever. So if you ever do that, take a video and send it to me. You'd have to have a really funny looking fishing rod. Okay. Now there is a not a sign convention. There's a naming convention that we're going to use for force vectors with unknown directions. So naming convention for force vectors with unknown directions. And so we're going to say that the force vector F subscript AB is the force on body A applied by body B. And the sad thing is, this convention is not universal. It seems to be the case that engineers use a convention like this, and physics people tend to use the convention that FAB is the force that body A applies to body B. So you have to be careful when you see this. You have to know what convention people are using. But in this class, that first subscript is always going to be the thing, the body that the force is being applied to. Okay. So in other words, you can think like, if you have a free body diagram of body A, all of the forces around it are going to have a first subscript in it. Okay, because it's the force being applied to that body. And this makes, so using this makes Newton's third law really easy to use. Because it just means that FAB is equal and opposite to FBA. And we're going to have a lot of cases where, if we have a structure that's made up of a whole bunch of different members in contact with each other, we're going to have to use Newton's third law all the time. Like, we'll isolate one of the members in this big structure, like a truss that a bridge is made on or something, and we'll have a force on A by B. And then when we isolate body B, we'll have the force on B by A, and we don't want to have two different vector variables we have to solve for. So instead we use Newton's third law. And when we isolate B, we just have the negative FAB on it. Okay, so now, anybody have any questions? Yeah.
So we definitely reverse the subscript as well as add negative.
For Newton's third law, yeah, that's what it means. It means, so if, right, so right, the force vector that's applied to body A by body B has the same magnitude and opposite direction of the force on body B by body A. We'll use that in some examples pretty soon. I just want to give a couple more sort of general guidelines before we go into that. One of the biggest areas of this class, one of the most important things in this class, is learning how to treat joints. So talk about contact forces applied by joints. So a first look at joints. So a joint is any connection between bodies. And later on, we're going to get into, hinges and pin joints and ball and socket joints and all these different ways you can attach two bodies together that allow certain types of motion and restrict certain types of motion. For now, in dealing with particle statics, we're only going to have 3 of these connections, and they're not going to be what you would normally think of as joints. They're just going to be ways bodies can sort of push against each other. So for particle statics, there are only 3 types. There are cables, and all those can do is pull between bodies. They're frictionless contact between bodies. And when that happens, the 2 bodies are pushing on each other. And then there's contact between 2 bodies with friction. Yeah, I'm sorry, I wrote the wrong thing. This should be frictionless. And then the third one is friction contact. And I'm going to just go through these 3 one by one so you know mathematically how to treat these cases. So first, cables. So a cable applies a force to a connected body parallel to the cable and away from the body. So for example, if you have a setup like this, where you have 2 masses hanging from the same cable that's going over a pulley. So let's call this box 1 and this box 2. And a free body diagram of box 1 has the weight down. I'll call that M1G. And the force applied by the cable is parallel to that cable, so up or down, and then it's going away from the surface of the body, so it has to be this way. And body 2, same idea. You have the weight down, M2G, and then you have force parallel to the cable, away from the body, and it's the same cable just going over pulleys, so it has the same magnitude as the first one. Any questions about that? Okay, next is frictionless contact. So if two objects push against each other without friction, then the force is parallel to the surface of contact, not parallel, perpendicular to the surface of contact. I'll give examples. And this time toward the chosen body. Okay, so let's say, so we have an incline, and there are two carts on the incline in contact with each other. Let's say this one has a mass of 5 kilograms, and it's in contact with this one that has a mass of 3 kilograms. And let's say there's a force of 100 newtons that direction. We don't know what that's from. It's just given. So first of all, let's identify where pushing contact is occurring. First, there's pushing between the surface, the incline, and the wheels. There and there. And then the two carts are pushing against each other along that surface. Okay, so the free body diagrams of the individual carts. First, I'll do the 5 kilogram. Okay, so what forces are acting? There's a weight force straight down. So 5 times 9.81 is 49.05. That's the weight. And then at the wheels of the 5 kilogram cart, there's a pushing contact. It has to be perpendicular to the surface. So perpendicular to that incline, toward the chosen body, so toward the cart. And I'm gonna act like it's all occurring at that one wheel because we're not worried about changes in orientation or anything. We don't care about moments yet. So I'll call this a normal force N5. And then the only other place that the outside world makes contact with the 5 kilogram cart is at the contact between the two carts. So that contact force is perpendicular to the surface of contact. So it's along a line like that toward the chosen body, so that way. And we don't know the magnitude, so I'll just call that R. And, this is what I was saying before when I was talking about what I want to see when I look at your homework and stuff when you turn in your binders. Um, no one would say that that's like a super careful picture, but you can tell from this picture that those two are perpendicular to each other and that this is not perpendicular or parallel to either of those. And then a free body diagram of the 3 kilogram cart. There's the outline. There's a weight force of 3 times 9.81, so 29.43. And then the incline is pushing on the wheels, so perpendicular to the incline toward the chosen body. I'll call that N3. And then there's that 100 Newton force, and we don't know what that's from. We're just told to put that in there, so that goes there. And then on the other side, there's a contact force between the 5 and the 3. So that's a pushing contact. We know it's perpendicular to the surface, so it has to be along that line, and it's toward the chosen body, so this way. And Newton's third law says it has to have the same magnitude as the force on the 5 by the 3. So notice the way I've drawn this, Newton's third law applies. This is F5 3. This is F3 5. They have the same magnitude in the opposite direction. So notice F5 3 is negative F3 5. Any questions about that? And then the last type is friction contact. And friction contact, when you deal with friction in physics 1, you usually know something about the coefficient of friction, and you know that the magnitude of the friction force is the coefficient times the normal force. In this class, we're not going to deal with that because we're always in a static case, which means that we can only use the coefficient of friction if we happen to be right at the limit of what the friction can be. And so instead of representing it as a normal force and a coefficient of friction, we're just going to treat this as a totally unknown force vector. So friction contact creates a force vector with an unknown direction. So for example, let's say we have an incline with one box. Let's say this is 2 kilograms, and then there's a 1 kilogram box on top. And let's say that there's a force, a horizontal force of 5 newtons this way, and a force of 10 newtons this way that's parallel to the surface. Assume there's no acceleration. Then a free body diagram of the 1 kilogram. There's a weight force down of 1 times 9.81. There's the horizontal 5 Newton force. And then in physics 1, the way you would treat this problem is you'd know what this angle was. You'd rotate your coordinate system so the x-axis is along that incline. Remember doing that. And the reason you would do that is because then you would have a normal force in the y direction and a coefficient times the normal force in the x or negative x direction, and it makes the math easier. In this class, we don't have to do that. We can keep whatever coordinate system we want because we're not going to break it up into a normal force and a friction force. So we can just represent this as an unknown force with whatever coordinate system we want. So this friction force, I'm just going to represent. So I draw my force component in the x direction, force component in the y direction, and I'm going to call this the force on the 1 kilogram box by the 2 kilogram box. Any questions about that? And now the free body diagram of the 2 kilogram box. We have a weight force down. So 2 times 9.81 is 19.62. We have this given force. We don't know where that came from, but it's 10. And now we have a friction contact between the incline and the 2. And so we're going to treat that as an unknown force vector. So there are the component directions. And I'm going to call that the force on the 2 by the incline. And then the only other place there's contact is up at the top where it's in contact with the 1 kilogram box. And so that's an unknown force vector. And it's the force on the 2 by the 1. And since we've already named a force variable F12, we might as well use Newton's third law here. Because so right now, to solve this, how many variables? Known. This is 2 variables. This is 2 more, so we're at 4. And this is 2 more, so we have 6 variables there. Okay. But Newton's third law says we know the relationship between this and this. So instead, this is 2, 4, and then we'll replace F21 with negative F12. And now that doesn't give us any more variables. and we have a system of 4 variables, but we have 2 equations from Newton's second law for this one, 2 more for this one. And so we have 4 equations, 4 variables, and we can solve for those forces. If we didn't use Newton's third law, we wouldn't be able to. If we didn't recognize that we could rewrite F21 this way, we have 6 variables and there's nothing we can do. So that Newton's third law idea is going to be really important. Yep. That's a good question. Right now, because we're doing particle stuff, the positions of nothing matters, the positions, because we're assuming all this is just happening at the center of mass. Later on, it'll be more important, but for now, just put it wherever it, makes it look the least cluttered. Any other questions? Okay, let's stop there. And next time I'll just go through a few examples. I'll assign a few problems like this and you can try to go through them. And if you have questions at the start of class, I'll answer your questions on them too. Okay, see you Thursday.